Okay, so welcome back. This is part 3 in our series on understanding transformers, and we've been looking at some of the characteristics of transformers, and here we've got a specific transformer we've been looking at, although these concepts apply to any power transformer. And we've got here a 117 volt to 12 volt transformer. And we've been looking at things like fusing. We've been looking at some of the characteristics that you may not be aware of these transformers. And ultimately, we're looking at developing a model, a computer simulation model, like we showed in the previous video, where we model some of the characteristics of these transformers, such as their nonlinear characteristics. In other words, if you apply a voltage much higher than the design voltage, you can get suddenly a lot of current flowing even on an unloaded transformer. And you can get a lot of harmonics generated, and noise and heat and everything else. So we've been looking at developing a model for this transformer. And in the previous video, we kind of made some assumptions and guesses about what we saw was the nonlinear characteristic of this transformer. And we came up with a model that we input to our computer simulation. And again, we can simulate these transformers in like LTSpice or Matlab Simulink, whatever simulation software you want. In this case, we're going to use software called ATP, since it makes it, in my view, a little bit easier to look at nonlinear characteristics. But anyway, we developed this nonlinear characteristic of the 117 volt winding of the transformer. And it's basically, you can see on the vertical axis, it's voltage RMS applied across the winding, and the resulting current in RMS flowing into that winding with the secondary open. So there's no load on the transformer. It's just a characteristic of the iron core transformer and the 120 volt or 117 volt winding inductance. So we use that, and we put that into the simulation and generated some results and checked them versus our bench test for energizing this transformer and looking at the transient that we get. So now what we're going to do is we are going to do some actual measurements of the transformer on the bench to get the actual curve, the voltage versus current curve for this transformer. So we're going to be applying voltage to the transformer, and we're going to go up to around 220 volts. Here we just guesstimated that our volt current characteristic, we guessed up to around 150 volts, but we're going to verify if that was accurate. And we're going to apply some very high voltages and look at the resulting RMS current flow and get a real curve, develop a real curve that we can put into our software simulator. And then what we're going to do, once we've got that in the simulation software, we're going to check it against the actual current flow we see in the transformer when we're applying, say, 220 volts. See if that matches up with the software simulation so that we know we've got a good model. So now in a previous video, we did a review of this variable transformer, which allows us to put 110 volts in, and it will give us 0 to 230 volts out. So this is like a perfect device for applying high voltage to our 120 volt transformer to see what happens, see what kind of current we draw. So we're going to be using this device to apply voltage to the transformer, and we're going to measure RMS voltage and RMS current. And again, the circuit we're going to use is a very simple circuit. Now when we look on the bench, it's going to look kind of messy because we're measuring so many things. But basically, I've got my variable transformer. This is going to go from 0 to 230 volts AC. I've got an on-off switch. And then I've got, in series with the primary winding, I've got a half ohm resistor, which we showed in the previous video. And the only purpose of that is to give us a voltage so that when current is flowing into this winding, it flows through this resistor, and we can get some differential probes across this to measure on our scope the visual wave shape of this current flowing into the transformer to give us a better idea for what it looks like. And we're also going to be measuring, like I mentioned, we're going to be measuring RMS voltage across this primary winding and also RMS current into the primary winding. And we're going to be using 2 multimeters for that. So when you look at all the bench stuff, it's basically just this. Okay, so here we are on the bench, and you can see I got a lot of stuff here. But again, it's very simple. The circuit I showed before, and you can see over here, I've got my variable transformer that's going to be applying 0 to 230 volts to our transformer. And here's our transformer. I've got my scope, which is going to be measuring the waveform of the current flowing into the transformer as you go from 0 to 230 volts. I've got 2 multimeters. This one's going to be measuring amps, RMS. This is going to be measuring volts, RMS, across the transformer. And here I've just got my on-off switch as before. I've got my half-ohm resistor with my differential probes going into the scope. Now, before we do this, I want to make it clear, do not do this yourself, okay? This is just for education to show you what you should get, but don't do this yourself. This transformer puts out 230 volts. It's very high voltage. You can get killed, you can get hurt, you can get injured. Do not do this at home unless you are qualified and know what you're doing. It can be very dangerous. Now, that being said, what we're going to do is we are going to apply from 0 to 220, say, volts across this transformer, and we're going to measure RMS current and volts. And what I'm going to do is I am going to video this so I can play it back later and see what the corresponding currents and voltages are so that we can generate our nonlinear curve. Okay, so just have to replay the video. You can do the same thing if you want. And then we're going to see on this scope the waveform, and we're going to expect it to have quite a few harmonics. Okay, so I've got my variable transformer. I've got it set to 0. I'm going to turn it on. It's on now. And I'm going to turn on the on switch to apply voltage to the transformer. And you can see I've got 0 volts. And I'm going to increase this. Now we've got 30 volts. We're starting to get a waveform on the current. So I'm going to bring it up to 120 volts, which is normal voltage. And here we are, 120 volts. We've got about 50 milliamps. And I think we showed that before. And you can see we've got a waveform. We've got a current waveform that looks a bit like this. And again, it's only 50 milliamps. So now what I'm going to do is I'm going to increase this and see what we get. So now I'm at 130 with 60 mils, 140 with 70, 150 with almost 0.1 amp. And now I'm up to 160 with 0.1 amp. And I'm up to 170 with 180 with 0.2. And you can see the waveform of the current is getting very distorted. And now I'm going to go up to, here we're at 200 and we've got 0.6 amps. And you may be able to hear the transformer humming because of the harmonics flowing. And I'm going to go up, and I'm up to 220, and I'm going to stop there. I'm over 1 amp. So that gives you an idea, and if we play this back, we can see the relative current and voltage. But you can see you're getting over an amp with 220 volts, and it's going to turn out that this is quite a bit different from what we assumed. So what we'll do is we'll go back and grab that data from the video and plot the curve and see where it puts us. Okay, so now I've gone back into Excel and I have, after replaying the video, I have plotted the volts and amps applied to the transformer as we go from 0 to about 220 volts. And that's what these two columns are here. So at 10 volts, I got 10 mils, 50 volts, I got 20 mils, and so on. And up to 220 volts, I have over 1.1 amps RMS. So then I plotted in this solid line, I plotted those values in a chart, volts versus amps, and you can see it goes way up here over 1 amp. In this dashed line, I have plotted what we originally thought was the saturation point of the transformer based on this curve that we just kind of guessed. We said around 140 or 150 volts it would go into saturation. So I just took this dashed line to show what a difference there is between the actual and what we guessed. So our guess was quite a bit off. So you can go pretty high on the voltage here without getting significant saturation. Now I also took a screenshot of the differential probe voltage across that 1/2 ohm resistor to get a feel for how much current was flowing, what the waveform was. And here is a screenshot of the current waveform at the maximum of 220 volts RMS. And you can see the vertical resolution is 0.5 volts per division. So it's 0.5, 1, and a little bit, maybe 1 1/4. So you recall the peak current should be twice that because it's a 1/2 ohm resistor. So there should be a little over 2 amps peak flowing. And we saw that it was 1.1, something like that RMS, so that makes sense. So here's the actual waveform. So what we can do is we can take that curve that we generated. We can take this curve, put it into a software simulation, and then run the simulator at 220 volts and see if we get the same waveform given this new characteristic curve. So here I am back with the software, and I will double click on this and you can put in the characteristic. I've already put in the characteristic of current versus voltage, and you can see up to 220 volts. I put 1.1 amps, and these pretty much match. I also added a 240 volt guess just to round out the curve. But anyway, this is basically the numbers that we got. So I've got that done. So now I should have a pretty good model. So what we can do is we can look at the voltage across this resistor to see what the waveform is going to be. So I'm going to run this, and it does the time step simulation, and I'm going to plot it, and I will plot the voltage across that resistor, which is this value right here. And you can see, let me clean this up a bit. I'm going to put the grid. Here is the initial transient. So what I'm going to do is I'm going to just take a subset of this and plot it. And you can see that the voltage peak goes up to 1.0, which is almost identical to what we've got here. Okay, if you put these side by side, you can see I've got 0.51. Here I've got 0.51. The actual is a tad bit higher in the peak, but you can see the waveforms look identical, and now we have a really good model. Even up at 220 volts, we've got a good model of this transformer nonlinear characteristic versus volts versus amps. So that's a pretty good verification that our model is good for this nonlinear characteristic. So that's it for this video. I hope it helps. Take care and have a really good day. Thanks.